Hi guys, so this is Chanya again. Welcome back to Math Learning Hub, a hub for everybody who loves math. So today we will be talking about the GCF and LCM of a number. This stands for greatest common factor and least common multiple, and we're going to go over what it is and how to find it. Okay, so let's start with GCF, right? So the GCF is, again, the greatest common factor that they have in common. So a factor is something that divides evenly into a number. For example, the factors of 18 are 1, 2, 3, 6, 9, and 18, because these are all the numbers that evenly divide 18. For example, if you take like 3, for example, 3 is a factor of 18 because when you divide 18 by 3, you get no remainder. So that's what a factor is. Similarly, 24, if you list up all of their factors, you can see that when you divide each of these factors by 24, and you divide 24 by each of these factors, you do not get any remainder. So that is basically what a factor is. So now I'm going to use these numbers to get the GCF. So the GCF of 18 and 24. So of course you could do this by listing their factors and then taking the greatest common factor they have in common, which is in this case 6. However, there is an easier way if you have larger numbers. For example, you can prime factorize the numbers if you want to get the GCF or LCM. So let's take an example where you have the numbers 96 and 112, and you want to find the greatest common factor or the GCF. In other words, the greatest factor that these two numbers have in common. So first, we're going to do something called prime factorization of the number, which will aid us in helping to find the greatest common factor. So I'm going to take 96 as an example to illustrate how to prime factor, right? So you create something called a factor tree, and you basically first write your number on the top, right? When you factor 96, prime factor 96, you write 96 on the top here. And then from that, you just figure out, okay, what are any two numbers that multiply to 96, right? What are any two numbers that multiply to 96? So in this case, we chose 12 and 8 because 12 times 8 is 96. Again, any two numbers will work. This is just the one we chose, okay? So then we draw branches off of 96 to the two numbers that multiply them, here and there. Okay, so now we take each of those two numbers and do the same thing, right? We say, what two numbers, let's take 12, right? Let's take 12. So what two numbers, when you multiply them, you get 12? Well, just any two numbers will work. So I picked 6 and 2 in this case. 6 and 2 here. Similarly, I looked at 8. Well, which two numbers will multiply to get 8? Well, again, any two numbers will work. So 2 and 4 multiply to get 8. Well, when I say any two numbers, I just want to clarify that any two numbers that are not 1, right? Because if you do like 8 equals 1 times 8, that won't really get you anywhere into getting the prime factors. Okay. So you keep doing this process. So you take 6 here because 6 can be divided into 2 times 3, right? 2 times 3 here. However, when you look at 2, you notice that the only two whole numbers that can multiply to 2 are 1 and 2. So what does this mean? That means that 2 is prime, right? 2 is prime. We're trying to get the prime factorization here, so we want all the prime factors. Therefore, since we already found a prime factor, we can actually just stop at 2. So you don't need to factor this one anymore. Same goes with this 2, but for this 4, this can be further split up into 2 and 2 right here. And after that, we realize that all the factors we have as a result are all prime factors, right? They're all prime factors. So now you take all the prime factors you have at the bottom, and these numbers, when you multiply them all together, it actually gives you 96. In other words, in this example, let's say you take 2 from here times 3 from here times 2 from here times 2 from here times 2 times 2. I'm just taking all the prime factors that we have, and when you multiply them, you do get 96, and you can verify that this is correct. So this is one way to express the prime factorization. An actual more efficient or easier to understand way would be actually 2 to the power of 5 times 3, right? 2 to the power of 5 times 3, because you have 2 multiplied together 5 times. 1, 2, 3, 4, 5, right? So 2 to the power of 5 times 3 is the prime factorization of 96. Okay. And you'll see how this will help in a bit. Now, since you're trying to find the GCF of 96 and 112, let's do the same thing to 112. Let's factorize, well, prime factorize 112, right? 96 and 112 here. So I will leave the factor tree from 96 up as an example, and I will let you guys pause the video and prime factorize 112, making a factor tree similar to how I did 96. Okay, hopefully y'all got a chance to work on this and you got an answer. So I'm going to scroll down to here where I've actually prime factorized 112 already. So I first broke it down into 112 is 56 times 2. Seeing that 2 is already a prime factor, well, I don't have to worry about this anymore, right? But I can still break down 56. So I chose 14 and 4, because 14 times 4 is 56, right? And since, of course, none of these are prime numbers and they can be broken down further, then I did break them down further. So 14 is 2 times 7, and 4 is 2 times 2. And these are all prime factors, so we don't need to break them down anymore, right? So now we take all the prime factors and then we multiply them together to get their prime factorization. So let's see, we have 3 2's, 1, 2, oh, actually 4 2's, 1, 2, 3, 4 2's. So that's 2 to the power of 4, right? Times 1, 7. So 2 to the power of 4 times 7. And that is the prime factorization of 112. So now that we prime factorize both numbers, we're actually going to find the GCF, which is what we've been waiting for. So we basically compare 96 and 112's prime factorizations, which are 2 to the 5th times 3 and 2 to the 4th times 7. And we basically take the highest power of the factors they have in common. The highest power of the factors they have in common. So for instance here, the only prime factor they have in common is 2, right? Because they don't both share a factor of 3. They don't both share a factor of 7. And we notice that the highest power of the factor they do share is 2 to the 4th, right? It's 2 to the 4th because this one has 2 to the 4th right here, and this one has 2 to the 5th. So the highest power that they share of a power of 2 is 2 to the 4th. And so you basically, that's just basically how you find your GCF. You take the highest power of the prime factors they share. And if there's more than one, you just multiply them all together. So basically the answer to this problem, the GCF would be 16 because 2 to the 4th is equal to 16. Now it's your turn, guys. I encourage you to pause this video and do these 3 problems. Okay, so if you guys are done, then I will go ahead and go over it. So this is problem 1, find the GCF of 36 and 42. And I'm just going to do this on the side. The first thing I'm going to prime factorize 36 and 42, right? So 36, I'm going to make a factor tree. 36 and 42, I'm just going to write them down for now. So I'm going to think, oh, okay, so what two numbers multiply to get 36? Well, the first thing that comes to my mind is 6 times 6, right? 6 times 6 over here. And then I need to notice, well, are these two prime? And then I'm like, no, they're not prime. You can break them down further into 6 is 2 times 3, and this 6 is also 2 times 3, right? And then I noticed, well, is 2 and 3 prime? Can I break it down further? And the answer is no, because they're both prime numbers. In other words, they share no factors except for 1 and itself. So since they're prime, I'm going to go ahead and circle them so I can just keep track. Okay. So 36 is basically, you have two 2's, right? So the prime factorization would be 2 to the power of 2, because you have 2 multiplied together twice. And then you have also 2 3's. So that's also 3 to the power of 2, right? And that is the prime factorization of 36. Now, if you go to 42, I'm going to make another factor tree. Let me separate this so you know this is completely separate. It's a different number. So 42, I'm going to think, what two numbers multiply to 42? Well, that's just 6 and 7, right? That's the first thing that comes to my mind anyway. Okay, and I'm going to check, are both of them prime? Well, I noticed that 7 is prime. 7 is a prime number, so I'm going to circle that number. But I know that 6 can be further broken down, so I'm going to further break it down. So 6 can be broken into 2 times 3, right? 6 is 2 times 3. And I noticed that 2 and 3 are prime, so I can immediately circle them and I'm done. So since we have 1, 2, 1, 3, and 1, 7, the prime factorization of 42 is 2 times 3 times 7. Okay, so now I'm going to use the prime factorizations to get the GCF, or greatest common factor. Well, I noticed that both of them do have a power of 2, right? They both have a power of 2. So once I notice this, I need to see, okay, what's the highest power of 2 both of them have in common? Well, this basically has 2 to the power of 1. This basically has 2 to the power of 2. So the highest power of 2 they have in common is actually 2 to the power of 1, right? Or just 2, in other words. Now I also see that they have 3 in common, right? They have a power of 3 in common. So what's the highest power of 3 they have in common? Well, the 3 here is basically 3 to the power of 1. This is 3 to the power of 2. So the highest power of 3 they have in common is just 3 to the power of 1, or 3. And when you multiply C together, you get 6, right? And that should be your GCF. So in other words, I'm just going to write it a bit formally. So GCF of the numbers 36 and 42 is equal to 6. The greatest common factor they have in common is 6. I just wanted to go back a little bit here. So the reason I didn't regard 7 in this multiplication is because this number, 36, it does not have a factor of 7, right? 7 is not a factor. I'm going to write that down. 7 is not a factor. So therefore, you don't need to regard it in the calculation of the GCF. Okay. So hopefully this makes sense. I'm going to move on to the next practice problem, which is find the GCF of 42, 16, and 72. Okay, so first, as always, the first step is to prime factorize the numbers. Well, we already have the prime factorization of 42, which is pretty convenient, right? Pretty convenient. But we still need the prime factorization of 16 here and 72. So I'm just going to do that. And hopefully by now y'all understand how prime factorization works. Oh no, what happened here? Hopefully y'all understand how it works. So I'm just gonna do it a bit quickly and then just talk through in the process. 72. Okay, so I noticed that 16 is 4 times 4. So these are not prime. I can break them down into 2 and 2 and 2 times 2, right? And I notice that these are all prime, in fact. So I'm just going to circle them all. And you notice that I have 4 2's. So the prime factorization of 16 is 2 to the power of 4. Okay. So for 72, and I'm just going to erase this and move it a little bit to the right. So 72, I'm going to break this down into 8 times 9, right? Then I ask myself, are any of these prime? No. So I can break 8 down into 4 times 2. I'll break 9 down into 3 times 3. I asked myself, are all of these prime? Well, I notice that 2 is prime, 3 is prime, and 3 is also prime. But this 4 right here can be broken down further into 2 times 2. Both of these are prime numbers. So therefore, since I have 3 2's and 2 3's, I can write this as 2 to the power of 3 times 3 to the power of 2. Okay, that was just quick prime factorization. So now I realize to find the GCF, I need to see which factors that all of these numbers have in common, right? Which prime factors do all of these numbers have in common? So we notice that all of them, in fact, do have, I'm going to use the red here. They do have a factor of 2 in common, right? We're talking about 42, 16, and 72. They do have a factor of 2 in common. Well, what's the highest power of 2 that they have in common? Well, this is 2 to the power of 1, 2 to the power of 4, and 2 to the power of 3. However, the highest power of the 2 they have in common is only 2 to the power of 1, right? Or in other words, it's just 2. And you notice that they don't have any other factors in common. For instance, even though both 42 and 72 have a factor of 3 to the power of 1 in common, 16 does not have it. And since we're finding the GCF of all 3 of these numbers, we can't include 3 because 16 does not have a factor of 3. So the same goes with 7. So the correct answer here should be the greatest common factor is only 2. Okay, so and finally, find the GCF of 360 and 225. 60 and 225, okay? So first, of course, the best way is to prime factorize both these numbers. So I'm going to make a factor tree here. I guess I'll keep consistent and keep using purple. So first, I'm going to quickly factor 360. I notice that 360 is basically 6 times 60, right? 360 is 6 times 60. So now are these two numbers prime? No, they're not. 6 can be broken into 2 and 3. Okay, I'll use green to circle them just for consistency's sake. Because I notice that 2 and 3 are both primes. That's why I'm already circling them. So 60, I'm going to break that down into 6 and 10. Well, are these prime? No, they're not. And I'm going to break them down further. 6 can be broken down into 2 times 3. 10 can be broken down into 2 times 5. Right? So are these numbers prime? Well, 2 is prime. So 3 is prime. And 5 is also prime. So now you have all the prime factors. So since you have 1, 2, 3 2's, so 2 to the power of 3, and you have 1, 2 3's, so times 3 to the power of 2, and then you have 1 5, so times 5 to the power of 1. This should be your prime factorization of 360. So now for 225. So if you memorize your perfect squares, which is very useful for both like TMSCA math, as well as like general contest math, as well as like high school math and middle school math as well, you can notice that 225 is 15 times 15, right? So now the question, are these two numbers prime? So no, I realize I can break down 15 into 3 times 5 on both 15s. So now I ask myself, are these numbers prime? Yes, they are. So 3 is prime, right? And 5 is prime because they don't share any factors other than 1 and itself. So therefore, since I have 2 3's, so my prime factorization would be 3 to the power of 2 times I have 2 5s, 1, 2 5s. So times 5 to the power of 2. That would be my prime factorization of 225. Now, if I wanted to find the greatest common factor of 360 and 225, I would figure out, well, which powers or which factors, prime factors, do they have in common? So you notice that they both have 3 to the power of something, right? 3 to the power of something. So what's the highest power of 3 they have in common? Well, they both have 3 to the power of 2, right? So the highest power of 3 they have in common is basically 3 to the power of 2. So we're going to write that down. 3 to the power of 2 times, well, I also noticed that they have 5 in common, right? A factor of 5 in common. So what's the highest power of 5 that they have in common? Well, this one has 5 to the power of 1. This one has 5 to the power of 2. So the highest power of 5 they have in common is 5 to the power of 1. And just to clarify a little bit more, the reason I take 5 to the power of 1 is basically because 5 to the power of 2 is 5 times 5, right? 5 to the power of 1 is only 1 5. So therefore, you can only take 1 5 and not both of them, because this one does not have 2 5s to give. And also, in general, if you have like a prime factor to 1 power in like the first number, like you have at 5 here, and then you have a prime factor to another power, or like that you have in 5 here, then you basically take the lower power. So take the lowest power of the factors that you do have in common, right? Okay, so going back to GCF calculation, so that should be it, because that's the only factors they have in common. So evaluating this, that's just going to be 3 to the power of 2, which is 9, times 5 to the power of 1, which is 5, and that's equal to 45. 45 here. Yep. So you notice how tedious this would be if you actually like listed out all of the factors, right? And so this is the power of prime factorization to find the greatest common factor. So I think at first I was going to talk about LCM, but I think I'll probably stop this video here since it's probably getting long, and I'll probably talk about LCM in the next video. Okay, so thank you all for watching, and if you have any questions, feel free to post in the comments. And if you want more content, then please be sure to like this video and subscribe to Math Learning Hub for more. Thank you for watching, and bye!